Aotearoa, kia ora, good morning, hello from me here in New Zealand. This is a follow-on from what I did by Zoom, and some folk didn't catch it, so I thought I'd put together this so you could have a grab of what it was I said. Just coming along here, moving along here, I want to use a plank to teach you talk about how to use a plank, even though it's a bit of a slur in Kumri. It's just a handy thing to have. I'm going to use a big lever. I'm going to use moments to find the mass of a plank. I'm going to use the plank to make a curved graph, linearize it, and find the equation. Practical one, levers, fulcrum, effort, load, the junior science area, class 1 and 2, but not class 3 levers, for obvious reasons shortly. So step 1, back a car onto a plank. I use a 3-metre scaffolding plank because they are small enough to fit into a vehicle, the longer ones do not. But this is big enough to be useful and small enough to be carried. A little wee thing I like to do is put a spacer underneath the plank so you can get your fingers underneath safely. In the old money, 10 inches in the old money, 250 odd millimetres, roughly sort of, around about, back the vehicle on, and you can see the safety block there is for finger space. Give a good lift. It's a class 2 lever. The fulcrum is on the ground at the front. The load is much closer in, and I'm way out there. So apart from the self-weight of the plank, which I'm only carrying half of in that case, I'm probably carrying about a 15 to 1 ratio of what's on the load there. Get the safety block for the finger space. I wonder if I can move this picture. Yes, I can. Move that out of the way. Moving along here. Get a student or a colleague to place the first spacer block. This locks in the lift. It also has the advantage of moving it shortly to a class 1 lever from a class 2. Just move along here. Place another smaller spacer block, and there's a reason for that, because it makes it into a better fulcrum. Change from a class 2 to a class 1 lever. You can see I look very, very elegant and classy right there. It would have been better if I walked into the close to the vehicle and then walked out on the plank and used my body weight, but I probably chose to do something a wee bit ungainly and foolish. However, it still works. I'm having trouble with my clicker here. So lift it and lock it in with another block, and now you can see the reason for the smaller piece of timber on the first block, because the sag of the plank means that there's enough room to slide the second one underneath. You can use whatever size bits of timber you have. It doesn't really matter. It just might mean if you've got thinner blocks of timber, you can have more steps. So lift it and lock it in with another block. Walk in, reduce the lifting moment, and the vehicle clunks down onto the front block. You can hop off quite safely then. Switch back to class 2 lever and get another smallish block. In this case, I put a piece of 150 by 50, or the old money 6 by 2, in between the 2 blocks that I had first. I want the smallest block on the top so I can provide a good fulcrum. So that's the class 2 lever to get that. And back to class 1, and then somebody can slide another piece of wood in underneath the front block. So put the block, lock it in, and get ready for the next lift. Walk backwards and forwards on the plank, hop off, hop on. It's a bit of moving around, but that's all right. It's kind of fun. And then I rinse and repeat and bring some smaller blocks of wood because that makes it easier to jack it up. The kids are quite taken with this. And then you can see me measuring how far up we've come, and I'll show you a closer look at that shortly. There we go, there's the tape measure. And you can see we haven't quite managed 300 millimeters, but I could have easily done that. The old money is about a foot, which is quite a lot. As you get higher up, the weight goes corner to corner on the vehicle, and it gets a little bit harder. You could stop at any point you prefer. A suggestion I'd make is reverse the steps before you go back to class so you can leave work and go home at the end of that working day. That's not a mistake I've made, but I would hate to make it. Practical number 2 is to find the mass of a plank using moments. I use both torques and moments because some curricula use the word torques. I prefer the word moments. I believe the Welsh curriculum does the same. Two main laws for equilibrium in two dimensions. The sum of the forces is 0 and the sum of the moments is also 0. So we'll find the mass of a plank with I forgot to put the word in known or calibrated mass. So step 1, find the balance point and mark it. And there you can see that I've got a bunch of troops around to help me, a little piece of aluminium, and on the table there I have marked my balance point, and I have also marked it with a small green mark from my whiteboard pen. Moving along. Step 2, move the plank sideways and then balance it with the 10 kg mass. This takes a bit of fiddling around, but that's fine. Suggestion I would make is to have a safety chair underneath the other end, because if something comes off, it could tumble and crash, and that's not preferred. Cool. I'm going to spot a bother here. Here we go, rightio. Now, to set up the moment, the torque equation, the little sketch of the situation simplifies things a bit. It's not quite a free body diagram because I haven't put in the upwards force from the fulcrum, but you could put that there. The moments balance, and it's not a complex situation. Swap sides, divide both sides by the measured distance to the plank, because we can use a tape measure for that. And then the weight becomes mass times g. And because we live in a non-zero gravitational field, it's okay to divide both sides by g. And you finish up with the mass of the plank being 19.2 kilograms. And then I use a set of bathroom scales to pick up the another way of measuring it. And we got about 19, and I was thrilled with that. That was kind of fun. Last practical is to make a curved graph, linearize it and find the equation. So teeter plank, put a bit of ballast on the plank, have it sticking out from a bench, and there's some measurements. Here's a photograph of the situation, the safety chair, which me pointing at it with a tape measure. And 3 things on display here. 1, you've got the 60 kgs of ballast, which I borrowed from the school's weightlifting gear in the gym. 2, the tipping axis above the edge of the table, so you can get access with it with the tape measure. And I'm pointing at that. And number 3, some ugly old geezer who likes playing with toys. And I don't know who that would be. And I can't spell with. Sorry about that. So here's a little picture again of the situation, and here's an extension. So the independent variable we're going to change is the weight applied. The dependent variable that we will measure is the distance from the table edge to the center of the applied weights, and I'm using the word weight on purpose. I'm using masses, but using 9.8 as the strength of gravity here. And so we put these numbers into a little spreadsheet, which I will do shortly. The theoretical overturning moment can be found from 4 things. The ballast mass, which is 60 kilos, the distance from the tipping axis, which was measured and on this chart shows 0.36 meters, the mass of the plank, which I got from a bathroom scales, and the distance from the tipping axis to the center of the mass, which I've drawn on there as 1.03 meters. Just move my picture here. This can be compared to the empirical overturning moment found from the transformed axes of the second graph that we've made. So here are the numbers put into a spreadsheet from the whiteboard. And here is the plot of the independent variable, weight in newtons across the horizontal, and the distance that you move the weight backwards and forwards to get the plank just a teeter in meters. And it's a nice hyperbola. So to linearize this graph is a good goal. So I put constant because physics teachers like the symbol K, and I thought, well, just English is important, but physics is important too. That'll do me. So linearize this. We're going to plot 1 over the weight on the x-axis of the second plot, and run through this again. So to linearize it, we extend the chart. I have copied the B column into D, and then I have found the reciprocal of the weight in newtons to the -1, and that looks about right. 3.92, 1 over that's a bit over a quarter. 49, 1 over that's a bit over a 50th. That looks good. That's a nice looking straight line there. I'm happy with that. and the kids can do it on a graph paper or Excel or something. And the line of best fit, and then we'll find the gradient. So I'm going to choose 2 points to find the gradient, and we don't use data points. We use points that are on the line somewhere, and I put a sunshine around those and made a little triangle. Now the gradient is the restoring moment of the system, and I'm going to go over that a little bit. But the gradient of this thing is 9.1. That's all right. It's pretty good. Now the units rise, which is meters, divided by the run, which is the reciprocal of newtons. Meters divided by 1 over newtons is meters Newton, or Newton meters. And we can see that the gradient is the restoring moment of the system because we have got the distance is equal to the moment divided by the force, because force times distance is the moment. The theoretical overturning moment of the system. Now, the plank was wet that day. It was the first day I brought it in, been out in the rain, and then bathroom scales gave 20 kilos. So the moment is the ballast mass times gravity times its distance, minus the overturning self-weight of the plank, its mass times gravity times the distance to its centre, give us 9.8 Newton meters, which is comfortably close to the 9.1 that we found empirically, and I'm really happy with that. If you get to 10% in a lab, you're doing pretty well, and I'm happy with that. Now, although plank is an insult in Cymru, Tupfel plank, and I hope I've got the pronunciation right because I've never been anywhere where anybody's spoken the Welsh, the Cymraeg. A plank can boost the fortunes of a physics teacher, and have some fun with it. It's good to have one around. It makes it bigger, and the kids can see it better, more interesting than a 300mm ruler on a bench. So thank you for letting me beam in from the other side of the globe. I'm a very grateful man, and the date that I put this in here is in 3 languages. The language of the colonizers and the 2 languages that we're doing our very best to save. And hats off to everybody working to save languages. I've had the most marvellous fun, and thank you very much for letting me take part. Let's see if I can finish this now without any problems. Thank you, everybody. Diolch yn fawr.